Okay, we should be good to go in terms of recording. All right. So this week we were talking about sections 1.6, 1.7, 1.8, 1.9, and 1.10. So yeah, do you want to just get started with the natural log and move forward, or do you have any specific questions, or?
Well, if you just wanted to go over what you wanted to go over, you may hit. I have a few questions, and if not, I can just ask at the end.
Okie dokie, let's do that then. All right, let's start with 1.6. So I'm on page 50. And we are going to just start by solving for t using natural logarithms. So let's start with question 2, which is 5t equals 7. And then let's do number 5, which is 10 equals 8t. And then let's do 12. Okay. So walk me through what I should do with number 2.
This is a natural log, right?
Yep.
All right, so it'll be, to bring t down, it's the ln of 5 times t.
So I'm going to put the t out front is equal to what?
The ln of 7.
Yep. So the important thing to remember here is take the natural log of both sides. And just to reiterate for people who are watching, what we did was we took the ln of 5t, and any exponent in a natural log can be moved out, so it's multiplied. So it's t times the natural log of 5. So after this, how am I going to isolate t?
You're going to divide both sides by the natural log of 5.
Yep. All right. And can I simplify this any further?
Well, you could use the calculator.
Yes. Okay. What I was getting at with that is sometimes people get confused. If you see something like this, 7 over 5, this is equal to the natural log of 7 minus the natural log of 5. And a lot of times people will confuse and conflate these two. So just be aware that this is not something that you can simplify, but this is. So make sure that if you're simplifying using the rules of natural logs, it is in the correct form. So yeah, so that is totally correct. We'll just do that again for these. Here, we do the same thing. What's up with this one? What's going to make this a little bit different from number 2?
Isn't the natural log of e always 1?
Yep. So if that is equal to 1, what we're going to end up with is the natural log of 10 is equal to t times 1, which is t. And then we can do it in the hypothetical. We just have a bunch of variables here. We'll do the exact same thing. This is kind of like a general case. So we'll have the natural log of a is equal to t times the natural log of b. T is equal to the natural log of a over the natural log of b. And so this is kind of just like generally like how one would solve a problem. It's exactly the same thing that we did in number 2 with just variables there. So we're pretending that a and b are numbers, and we're solving for t. Okie doke. So let's do let's try to do number 16 too, which looks like this. All right. So this is going to be a little bit more involved with like the rules of logs. First things first, we're going to take the natural log of both sides. We're just going to treat it like we did the last one because we're looking to solve for t. So we'll end up with the natural log of 5e to the 3t is equal to the natural log of 8e to the 2t. First thing, what do you think we should do?
try and isolate probably e to the 3t to divide by the natural log of 5.
Well, this is the natural log of all of this, right?
Oh,
because I took the natural log of this whole.
Oops.
So first things first, we're going to bring down this exponent because that's just going to make things really complicated. And by taking a natural log, we can do that. So we can call this 3t times the natural log of 5e. And this is going to be 2t times the natural log of 8e. So yeah, sometimes putting the parentheses in where they need to be can help determine exactly what's up here. Okay. What is next?
Trying to isolate the t's.
Mm-hmm.
So
let's go ahead and split up these logs here, right? Because this is something that's multiplied. So we have something times something here, which means that this can be the natural log of 5 plus the natural log of e, right?
Okay.
And so we have that times 3t is equal to 2t, and then we can turn that into the natural log of 8 plus the natural log of e, which we can then rewrite because we know the natural log of e is equal to 1. ln 5 plus 1 is equal to 2t ln 8 plus 1. And so the issue is, if we were to divide by t here, we would end up by losing the t that we have, right? So we're trying to find a way that we can actually solve for t. I haven't solved this problem in a hot minute. I just saw it and thought it would be a good one to try. So I'm not entirely sure how this is going to play out, but we're going to just solve it using the rules that we have. So I'm going to distribute this t, this 3t. So I can start using addition and subtraction instead of dividing out that t. So I don't know if I want to do that. Yeah, that might not be the best plan. Okay. So let's instead. Sorry, sometimes you hit a problem and it's just like not exactly the easiest thing to solve. So instead of doing that, maybe we should try rewriting it like 3t is equal to 2t ln 8 plus 1 over ln 5 plus 1. Then you know, I don't like that either. So we're going to keep going on this vein right here. We're going to turn this into minus 2t minus 2t. So we'll end up with 3t ln 5 plus just t is equal to, here we go. Yeah, so we have 2t ln 8. Then let's subtract 3t ln 5 minus 3t ln 5. So we end up with t is equal to 2t, the natural log of 8, minus 3t, the natural log of 5. And we still haven't multiplied it. what do you think? What do you think that our next approach should be?
I'm trying to figure that out, but
Why don't we try to go back to the beginning?
all right, let me flip a page over and start over.
Sorry. I jumped in here thinking that we could just use the natural log and that would be the easiest way to solve this, but what if we didn't do that? So what if instead of doing that, we divided each by e to the 2t? So this would turn into, what does it look like when you have exponents and you're dividing an exponent that has the same
reciprocal?
Yeah, so this would be like saying this is 5e to the 3t times 5 times e to the 3t times e to the negative 2t. So these would cancel out here. What is the rule for the exponents in this like setup? Like when you're multiplying, what do you do to these?
You add them.
Yes. So what would I end up with? I would end up with 8 is equal to what?
5e to the t. Exactly.
So this is where I went wrong. I jumped in and took the natural log right away, and the point of this problem was to not do that. Instead of doing that, I should have seen that it was easy to divide and get rid of make this a simpler problem to solve. So now I have a problem that looks like this. We can solve that really easily, exactly like we did number 2, number 10, or number 12, or whatever. So that would be the natural log of 8 is equal to natural log of 5 e to the t. Natural log of 8 is equal to natural log of 5 plus natural log of e times t. I just split these up right here because they're multiplied. So I'm going to end up with the natural log of 8 divided by, or not divided by, natural log of 8 is equal to the natural log of 5 plus t. So it'll end up being the natural log of 8 over 5 is equal to t, because this will be natural log of 8 minus natural log of 5, which I can translate to that. Another way I could set that up, and how I know that I did how I did this right and I ended up with the correct answer, is that I could go back up to here and say that that is equal to 8 over 5 is equal to e to the t, and then I could just take the natural log right there. So it'll be natural log of 8 over 5 is equal to natural log of e times t. It's 1.
Okay, so I did do it right because that's what I did.
Yeah. So these are like 2 different ways of breaking it down. But yeah, so I think the lesson here is that I jumped the gun. Yeah. But is it what?
No, that's okay. This one just kind of confused me, but that's okay.
Which means I also did something wrong in this over here with the green. I made a mistake in that I pulled this out of this 5e without divvying this up. What I should have done is made this the natural log of 5 plus the natural log of e to the 3t. This is a bad way of solving the problem, this whole thing in the green and blue. But I did screw up most notably right here by not doing that.
So I just want to make sure I have the simplification right. So t would also be equal to the natural log of 8 minus the natural log of 5, right?
Yep.
Okay.
This is also a correct answer.
Okay.
The reason that you want to know these log rules and know that this also equals the natural log of 8 over 5 is because on a multiple choice test, you might have this one or you might have this one. And you just want to make sure you know that those are the same thing.
Okay. So you want to simplify it using the rule?
Yeah.
Okay.
I mean, like, I always try to find like the simplest answer, but I mean, sometimes on multiple choice tests, they don't necessarily have the simplest answer. They just have like a good answer, because simplifying would take time. So, yeah.
Yeah, I'm not gonna lie, I'm nervous about the midterm and the final. Like it, and I'll send an email to the professors. Like, if you have to memorize the formulas or if they have like a reference, so you just have to be able to recognize it.
The simplification of natural logs and this type of stuff with exponents, that is stuff that you're going to have to memorize.
Okay.
And a lot of the other stuff, when we're getting into like doing derivatives, it'll come with practice. The more you practice, the more likely it is you'll just be able to do it like by muscle memory, basically. But that's stuff that all of the times I've GSG'd for this class previously, that's been required that you haven't memorized.
Okay.
Okay, so after I screwed up there, let's try to do another problem from this section. Let's do number 26. So this here, we have been given problems. Let's do we'll do number 18 and number 26. We're 8, or no, that's not. We should do 22 and 26, not 18. Sorry, I was looking at the wrong bracket. So basically what is going on here is that in 22, we have something that's written in this form, e to the negative 0.5t. So this is p is equal to p naught e to the negative k, or e to the kt, right? And then in this one, we have something that's written in the form p is equal to p naught a to the t. So we're trying to move between these, trying to read the right problem here. That's 1.7t. We're trying to move between these. And this is a really important skill to develop because I know it may not feel like it now, but you really do want to have your anything in the form of e to the kt, just because later on it's going to be a lot more convenient that way. And we're going to use the same type of like skill later when we're actually taking derivatives in like a month or so. So this is like an important skill to develop. So what would you say about taking this into the other form? So right now it's p is equal to p naught e to the kt, and we want to take it into p is equal to p naught a to the t.
I'm just writing this down. Maybe let me. Isn't this where you want to take the natural log and move everything down first?
I think first what I would do is kind of establish what I'm trying to accomplish here.
Oops, I miswrote it. Oops. There we go.
So I would say I see these two equations, right? And I see that they are equal. So I would say that p is equal to p naught e to the kt, and it is equal to p naught a to the t, right? So we've established this equivalency, and now we can forget about the p because we don't need to worry about that. Instead, we have this. We can divide both sides by p naught because the initial value isn't going to be changing, and we're going to end up with e to the kt is equal to a to the t. So what does this tell us? We have something that we can work with here right now, I guess. When we have this, we know that this is e to the kt, and we just want to turn this into a. So what we're trying to find here is a. And we're leaving t as a variable. We're not worried about turning t into a number. So if I have e to the kt, or rather e to the negative 0.5 t is equal to a to the t, I can solve this by saying this is the natural log of e to the negative 0.5 t is equal to t times the natural log of a. So this turns into negative 0.5 t is equal to t natural log of a. These t's we can divide out. So now I end up with negative 0.5 is equal to ln a. What am I going to do to find actual a?
Plug it back in.
Where? Because now I have like the variable that I'm trying to find is right here.
Okay.
So how do I undo a natural log?
Can you make it the exponent? No. This
Yeah.
is where I get confused.
Yeah. Just like for future reference, think of, we have like addition and then we have subtraction, right? And they're like inverses of one another. If I like were to start with 0 and then add 1 and then subtract 1, I end up with 0 again. So they undo one another basically. And the same thing with multiplication and division. And then you can kind of think of natural logs and to the power of e as doing that as well. So the way that you would undo this sort of natural log is to say this is e to the power of 0.5 is equal to e to the power of the natural log of a, and e to the power of a natural log is equal to that number. So a is going to be equal to e to the 0.5. Another way you could look at this is through rules of exponents. You could say that e to the kt is equal to e to the k times e to the t, right, is equal to a to the t. Or rather, yeah, that's not correct. That's not correct. That was incorrect. I screwed up my rules of exponents. I'm sorry. When these are multiplied, if I were to have e to the k times e to the t, this would be e to the k plus t, as we just established. In order to get it in the correct form, it would be e to the k to the t, right? So taking the power of something that's been taken the power of. And then what we could say is that if I have e to the k to the t is equal to a to the t, then e to the k must be equal to a for these to be the equivalent, right? So e to the k is equal to a. And in this case, k is equal to negative 0.5. So that's our answer. So there were kind of two ways of solving that. There is making that equivalency, and then also going through and taking the natural log to determine exactly what a is. Did that make sense, walking through that?
Sort of. I thought I maybe understood it better before, but...
Oh, no. Okay.
Don't worry about it, because I have anxiety over math anyway. That's why I try and make all the lectures and I do all the homework.
Yeah. Why don't we try to walk through this one? We're going to do the exact same thing.
Okay.
So first things first, what form is it in, and what form do we want it in?
It's in a p naught a to the t.
Yep. What does this mean that we're looking for?
T is how many years?
That can be true. In this case, it's just generally given to us as a function, just like an exponential function. So we're not really concerned with what is actually happening here. What in this equation, what are we solving for it ultimately? If we want to turn this into this form of p naught e to the kt, instead of a to the t.
We're looking for the constant. Okay.
So we want to find k. So we're gonna make this equivalency again. We're gonna say p is equal to p naught a to the t, which is equal to p naught e to the kt. So I don't have to worry about p naught at all because it'll just cancel out from both of these equations. So I have a to the t is equal to e to the kt. So as we established from right here, right? A is equal to e to the k. So if I have a and e is just a number, right? E is like 2 point something.
2.71.
Yeah. Then what can I do?
Take the natural log.
Yeah. So I'm going to go ahead and substitute this in. This will be 1.7 is equal to e to the k. I'll take the natural log of both sides. So I'll end up with the natural log of 1.7 is equal to k times the natural log of e, right? So k is equal to the natural log of 1.7. So in order to write this in this form, I would say p is equal to, p naught here is equal to 10. So 10 times e to the natural log of 1.7 t. Does that kind of make a little bit more sense?
I'll get there.
What is it that's kind of tripping you up?
It seems like what, I don't know, it just seems like you're going more in depth on the homework problems, and I'm trying to figure out the midterm and final, like if they're going to go in as much depth as some of the problems, because some are really superficial and skim the surface concepts.
Yeah.
And problems like the last one really dig in.
So what I tend to do in these sessions is I kind of want to like approach the why does this work? Because like I guess I'm the kind of person, I just don't like taking things at face value. So if I were to tell you e to the k is equal to a and then not explain it, that I would feel like isn't like underserving you. But I mean, like, as long as you like walk away with like knowing what's happening and like being able to follow it, I think you're in a good position. So do you want to try another one of these?
We can. Like, no, I like the why behind the what too, but at the same time, I'm trying to phrase this delicately. I'm not a math major, and this is like probably the most advanced math class I'll have to take. So whereas if I was going on for more mathematics and like statistical interpretation and stuff, I know I would have to dive into the details and be able to switch it around a lot more. Does that make sense?
Yeah, I totally get you. Just for me, I'm also not a math major. I mean, like, this is just something that I enjoy like doing. But yeah, the reason I do it like this is because I'm hoping that if you understand why, if you forget something, you'll be able to have the tools with you to derive it. For instance, if you forgot that a is equal to e to the k on an exam, I would like to have gone over like exactly how to prove that a is equal to e to the k, and therefore you would have like the tools to problem solve.
Oh no, I understand. Like, my frustration right now is like when I get into the situational, like compound interest versus annual interest, I can work them. So it's like, and I've been working on refreshing my basics. It's just, that's where my disconnect is. And I'm trying to put it all together. Cause like, I'm like, why can I solve these problems? But sometimes with the most basic stuff, which I need to solve these problems, I get frustrated.
Yeah, no, that never really goes away. Sorry. I mean, like, you saw me screw up on that last problem. I've done this material so many times, and yet I do screw up on like small things every once in a while, and that's just kind of, it's like frustrating to like not necessarily be like on top of everything all the time, but that's just kind of the nature, I think, of some of this material. It's like not easy. So yeah, practice is really all I can say. Do you want to try to do some from 1.7? We're going to talk a little bit more in depth about this kind of stuff.
Yeah, sure.
Do you have any questions about 1.6?
No, I was pretty good in 1.6.
Okay. So 1.7 is talking about exponential growth and decay. We should start. Let's start with number 2. So we're on page 57. The exponential function y of x is equal to c e to the alpha x satisfies the conditions y of 0 is equal to 2 and y of 1 is equal to 1. Find, so it tells us exactly what it wants us to do, c and alpha, and I forgot a d there, and find y of 2. Okay, so this is a kind of problem that would perhaps show up on an exam. What is your first like gut instinct when you look at this? Like, what do you want to do first?
Probably substitute in.
Mm-hmm. What are you going to substitute in?
That's what I'm trying to figure. The exponential function, got that. Find the constants c and alpha. Okay. So when y is, probably use y as 1, so then it would be...
So you want to say y of 1 is equal to 1, so that is equal to c e to the alpha x?
Mm-hmm.
Okay.
Yep.
We're going to have an issue here.
Oh, great.
Sorry. The issue is that we have 2 unknowns.
Yeah.
Right? We have c, which is a giant question mark, and we have alpha, which is a giant question mark.
Yeah.
The way that we do that is by going back to originally what we think. So if this is of the form p is equal to p naught e to the kt, right?
Mm-hmm.
What is p naught? Like in words, like what would p naught be? If we were talking about like a population, for instance.
That would be the starting population at the beginning of the study.
Right. So what does this mean in terms of math? Starting number is when time is equal to
0.
So we could say, and this would be true, p of 0 is equal to p naught.
Mm-hmm.
Do we have an analog for that in this?
Yeah, 2, because y of 0 is equal to 2.
Which would be equal to?
Then the 2 e alpha x. No, this is where I suck at
Nope, this is good. We're just going to do right here. We have y is going to be the equivalent of p, right? And then we have p naught e to the kt. So if p of 0 is equal to 2, then it is equal to p naught. So we can do the exact same thing here. We can say that y of 0 is equal to 2, so 2 is equal to c. And the way that we can show that in like math is if we say y of 0 is equal to 2, is equal to c e to the alpha and then t is going to be equal to 0, right?
Yeah.
So 0. So we'll end up with 2 is equal to c, e, and then alpha times 0 is 0. And what is any number to the 0 power?
1.
Yep, so this will be 2 is equal to c times 1, or 2 is equal to c. So we either start by substituting in this t is 0, or we can just go ahead and say, I know that y of 0 is equal to 2. That's my initial value. That's my starting number. That's my p naught. In this case, in the lingo that we're using, it's going to be c. Okay, so now that we've gotten that out of the way, we can rewrite this. We can say this is y of 1 is equal to 1, which is equal to, I have c now, so I can say this is 2, because c isn't going to change, e to the alpha x. And now I only have one variable. Right? So I can go ahead and solve. So 1 is equal to 2e to the alpha x. I can divide both sides by 2 because I want to get that constant out of there. So 1/2 is equal to e to the alpha x. I can go ahead and take this natural log. So this is natural log of 1/2 is equal to natural log of e to the alpha x, which is equal to alpha x. I can do that, right? I'm pretty sure I can do that. So,
isn't the natural log of e 1, so wouldn't it just be log of 1/2 equals alpha x?
Yes. See, here's my problem. I left x. So as we decided up here, if we're taking y of 1 is equal to 1, then this is not going to be x. This is going to be 1.
Yes.
So this is going to be times 1. I was like, something's wrong here. So that's alpha times 1, which is just alpha. So we have 1/2 is equal to e to the alpha. So this will be the natural log of 1/2, which is equal to alpha ln e. So this will be alpha is equal to natural log of 1/2. All right. Our next step is going to be putting this in our last problem. We found c, we found alpha. All we need to do is put it together. So to find y of 2, we need to say that we have 2 times e to the natural log of 1/2 times x, which is going to be 2. So we would, simplify this however, but I don't think we need to. This is a number. This is going to simplify down to a single number with your calculator. Does all of this make sense?
Hold on 1 second. C is 2. Where did you get the 2ln of 1/2? And that's e.
I said that this is equal to alpha. So this is c, this is alpha, and this is x.
Oh, so okay, that's right. Never mind. Yeah, I got it. Sorry.
No, you're good. And I am going to say, and this is for exams mostly, this is something that they do on exams. They will, instead of writing ln of 1/2, they will simplify it. They will say this is equal to the natural log of 1 minus 2, or the natural log of 2, sorry. What is the natural log of 1?
0, isn't it?
Yep, so 0 minus ln 2. So the natural log of 1/2 is equal to negative natural log 2. So sometimes instead of saying natural log of 1/2, they will just have it written as because they don't like the fraction in the So yeah, that's just an FYI that they'll do that. But usually you can just go ahead and use your rule of logs. Do you have any questions about this problem?
No, I got it. I just feel like I fumble when I'm trying to explain it because I understand it on paper, but trying to...
Yeah, that's always, I mean, that's the hardest part. Okay, let's do problem 8. So find the doubling time of a quantity that is increasing by 7% per year.
Okay.
So we're going to have to break this down into what everything means.
Yeah.
Let's just go ahead and start with our first p is equal to p naught e to the, or rather, should we use e to the kt or should we use a to the t?
Give me a sec. Because I know if you're doing doubling time, it's 2p equals 1. Wouldn't it be e to the kt?
Yeah, we can start with that. And we are doing doubling time, so you're right. This is going to be p is equal to 2p naught. So this is indicating that we're double. So I can go ahead and put this in as p 2p naught is equal to p naught e to the kt. I can get rid of p naught on both sides. So I have 2 is equal to e to the kt. Now, how do I say that it's doubling at a rate of 7%?
It would be, well, probably should have used a to the t because if it's doubling at a rate of 7%, well, wait a second, hold on. I'm getting ahead of myself trying to explain it.
No, you're actually right. This is exactly, I would use a to the t because then a can equal 1.07. So this is 2 is equal to 1.07 to the t. So I input my information about doubling. This is doubling. I input my information about how fast it is increasing. How do I find what I want? And what is it that I exactly want?
Do number 8. Let me reread it. Find the doubling time per year. You want to find out how long in years or fractions of years it's going to take for p naught to double.
Exactly. So what exactly am I looking for? Looking for t.
Yeah.
Okay. So how would I solve for it?
You would take the ln of 2 equals t multiplied by the ln of 1.07.
So t is equal to ln 2 over ln 1.07. Precisely. All right. Do you have any questions about what's happening in 1.7? Sorry, we have like 3 more sections to get through yet.
No, that's fine. That's totally fine, yeah.
So we're going to go ahead and do some from 1.8. So this is on page 63. I think the big takeaway from this chapter is being able to like pick out functions within functions, which is going to really come in handy in the future. So we're going to start by we're going to do problem 2, which is given f of x is equal to x minus 2 and g of x is equal to x squared plus 8. They want us to find, actually we're going to probably do 2 and 4, but they want us to find a, they want us to find f of g of x, g of f of x, and then f of x. Okay, so do you kind of get what's going on in this chapter?
Yeah, I kind of get it. And I know I need practice, so if I verbally fumble, I'm sorry.
No, you're fine. That's like why we're here. Um, so when I write down, like I'm trying to find here, I'm trying to find f of g of x, what is my first step?
First, I write down what the f of x is so I know where I'm going to plug g in.
So here's my f of x.
So then where the x, in the x minus 2, I'm going to substitute x squared plus 8 minus 2.
Yes, exactly. So we're pretending this x is this whole function g. So this is going to be equal to x squared plus 8. And I can put it in parentheses, but it's just to the first power, minus 2. So x squared plus 8 minus 2 will be plus 6. And that is that. What about for this next one, g of f of x?
So in g of x where it's x squared, you would substitute x minus 2.
Yep. And I don't really feel like pulling it all out. You'll end up with a polynomial.
Yeah.
But I don't think that's the important takeaway. All right. So finally, if I have f of x,
Wouldn't it just be x minus 2 minus 2? Like, and then you simplify it, which is x minus 4.
Yep. All right. So that's like basically what's going on here. Let's do number 4 too.
Okay.
So here we have f of x is equal to x squared, and g of x is equal to 3x minus 1. And we've got a bunch of different things to find. To start with, we need g of 2. That's wrong. That's one down. Sorry. This is going to be f of 2 plus g of 2. So where are we going to start here?
So wherever you see an x in f of x, you put a 2, so it would be 2 squared plus 3 times 2 minus 1. So it would be 4 plus 6 minus 1, which would be 9.
Yep. So this is going to be 4 plus 5, 9. Okay. Now let's try to do B. So here we have f of 2 times g of 2. And we already found out what f of 2 and g of 2 are equal to, right? So we can just use those. We can say that f of 2 is equal to 4. And this is times g of 2, which is equal to 5.
Which is 20.
Right. So, C, we have f of g of 2. What's up here?
F. So wherever the g of 2, which is 5.
So if I just go ahead and say g of 2 is equal to 5, then this is equal to f of 5, which is equal to
the f of 5, x squared.
So it's equal to f of 5, so it'll be 5 squared.
Okay.
So we just plug it right back into f of x. So 5 squared, which is
25.
All right. And then this last one is going to be g of f of 2. Oh, go ahead.
I'm trying to think, hold on. So wherever there's f of 2, so would it be, hold on. The function of 2 is 4. So then wouldn't it be 3 times 4 minus 1? So it'd be 12 minus 1, which is 11.
Exactly. All right. So the important thing here is to break things down. So we're going to do just one of number 5.
Okay.
So that you can see it with a little bit like different like frame. We're going to do 5a. So if I have this function g of x is equal to x squared plus 2x plus 3, and they want me to find g of 2 plus h, what am I going to do?
Everywhere you see an x, you're going to put 2 plus h.
Yes. So g of 2 plus h is equal to 2 plus h squared plus 2 times 2 plus h plus 3. So I'm going to separate this out. So this is 2 plus h times 2 plus h plus 4 plus 2h plus 3. So this is 4 plus 2h plus 2h plus h squared plus 2h plus 7, which is equal to h squared. And then I have 2h, 2h, and 2h, which is 6h. And I have 4 and 7, which is 11. And this is what it ends up to be. So that is what g of 2 plus h is equal to.
Hold on. So I'm just, hold on, just took me a second longer. Hold on.
You're good.
Squared plus 6h. I got it. Okay.
Okay.
H squared plus 6h plus 11.
Yep.
Yep. All right.
All right. So exactly. Let's try to do some from 1.9. So what's going on here is, oh, here. Let's be on page 69. Section 1.9, and let's do 2, and let's do 4, and let's do let's do 9, and let's do that for right now. So 2 is going to be, we have a function that looks like this. 4 is going to give us a function that looks like this. And 9 is going to give us a function that looks like this. So it wants us to determine whether or not this is a power function, and it wants us to be able to write a power function in the form y is equal to k x to the p. So basically how they're defining a power function is something that can be written into this form, right? If it can't be in this form, then it's not a power function. So what would you say about number 2?
I don't think so.
This is a matter of like rules. We say that the square root of x is equal to x to the 1/2.
Yeah. Oh, okay.
So if I rewrite it like that, I end up with y is equal to 5x to the 1/2. So k is equal to 5 and p is equal to 1/2.
Oh, okay.
And it's a power function.
Yes.
So for this one, what would you say here? Power function, yay or nay?
Yeah.
How can I rewrite it? And what is k and p?
So hold on. Wouldn't this be, hold on, 3 over x squared? Isn't that 3 also the same as 3x to the 1/2?
Not to the 1/2.
Or to the -2?
Yes, to the -2. So yeah, 1 over x to the 3rd, let's say, is equal to x to the -3. And so whatever number this is, as long as it gets turned into a negative sign, it can be moved up top. So that's what it looks like. Here's k, here is p. Yes, it is a power function. Okay, what about this one, number 9? Yes or no?
Wasn't like 5x? Let me see. 3 times, hold on, 5x. Wouldn't it just be, well, 3 times 5x? Isn't that just 15x? Wait,
No, 5 is to the power of x, but the 3 is not.
Oh, okay.
So the three is not a part of the base.
Oh, okay.
So are you thinking a yeah for a power function or no?
I'm thinking a yeah, but I want to say if I look back in the rules, there was something about.
Let's go ahead and treat it like a yes.
Okay.
Let's find what is k and what is p.
K would be 5.
Okay. And what is p then?
Then P would be X, the unknown.
Yeah. So the issue here is that means that we can't put it in this form, right? So you could also say, like, what if k is equal to 3? So k is this constant that's out here, right?
Yeah.
So this is a constant. That could be called a k.
Uh-huh.
And then in a power function, we have a base that is x, and this is a number.
Okay, that's what I was saying, because X was the exponent and not the base, that it wouldn't fit.
So because x is in the exponent, we can't say that p is equal to x because that doesn't fit our rule here. We want p to be a constant. So in order for it to be this power function, it needs to be
Known or a constant.
Yep. So the issue here is that we have 5 to the x instead of x to the 5, for instance.
That's what I was saying, because even though there was an exponent, I knew there was something with like X being an exponent that was like no.
Yep. So it makes it a little bit more wonky. Okay, let's try Let's try question 16. So this is kind of physics-y. The gravitational force F between two bodies. So we have F, and we're trying to relate F to D. So it is inversely proportional to the square of the distance between them. So how would I start breaking this down?
Hold on. So don't you want the inverse of D squared?
Yep. So it's inversely proportional, which means D is going to be on the bottom. And it is the square of the distance. So it's d squared. So one way that you can put that in k. There's k. I sometimes write it like this, and I use like alpha to like show like proportionality, but I haven't seen that language used, I think, very much before. But basically what I'm saying is that they can be related in this manner. So for instance, if d was to go up, then 1 over d, or d squared would increase, so d squared would get larger. 1 over d squared would get smaller because we're dividing by a larger number, so force would get smaller, which makes sense because if you're pulling two bodies away from each other, they won't exact the same amount of gravitational force, they'll exact less. Does that kind of like, that's okay?
Yeah.
All right. All right. Let's try to do some from periodic functions. This is really gross. Everyone hates this chapter. A lot of people who have come into this class before have said that they have not seen trig in like forever, basically. The good thing about this is that you will only need to know as much trig as is brought into this chapter. Okay. And when we move forward, trig will not be discussed as it is in this chapter. We're using these functions. You have to understand that a sine function is a function, but it doesn't behave like, you don't have to like calculate exactly like what the wave looks like, that sort of thing, in really any other like part of this class. Okay. So this is the worst of the trig.
This wasn't that bad, but my stumbling block is when I went through the videos and stuff, was figuring out the period. Like when I was doing my homework last night to prepare for today and to get the homework done, I totally drew a blank and got frustrated and went to bed.
Yeah. So the important thing is to break it down. If you have a function that looks like y is equal to a sine bt plus c, we know that a is going to be amplitude. We know that b, we know that period is equal to 2 pi over b. So they're related, but they're related inversely. So that's where b is going to come in useful. And then c is going to be our vertical shift. So if I have a problem, like for instance, number 6, I have something that looks like this. Y is equal to 4 cosine 1/2 t. And we're just trying to find the amplitude and period. Amplitude, what is that?
Amplitude is 4.
Good. We got that out of the way. Then what is period going to be?
That would it be pi over 2? Or 2 over 2 pi? This is where I understood it, and then I don't know what happened. I totally lost.
You're fine. So it'll be pi over 2 over b, or not pi over 2. It'll be 2 pi over b, right? And b is equal to 1/2. So it'll be 2 pi over 1/2. And if I divide something by 1/2, it's like multiplying by 2. So I can move this from this all the way up. So it'll end up being 4 pi. And that is my period. Okay. So using those like equations is kind of.
So for like number 1, y equals 3 sine x, to find the equation, amplitude, would the period just be 2 pi then?
Yep. So the amplitude is going to equal 3, and the period is going to equal 2 pi over 1, which is just 2 pi. And that makes sense. It jives with what we have for a graph. if I have a graph of a sine wave, it looks something like this. That's a cosine wave. Whoops.
I'd say that was cosine.
It looks something like this, right?
Mm-hmm.
And so our standard sine wave, our generic, this is just sine of x,
Mm-hmm.
is going to look like this. 2 pi, 1 period, height of 1, or amplitude of 1. So it goes from 1 to negative 1.
Mm-hmm.
So here's our amplitude.
So then for 3, negative 3 sine of x, negative 3 is the amplitude?
Yes. So for 3, the amplitude
means you would just flip it over the x-axis. And then the period would just be, is that 20 or 2 theta?
That's 2 theta. So we're pretending theta is the variable here, like x. So our b is equal to 2.
Okay.
So what this would look like is we would flip it over, right? Just like you said.
Mm-hmm.
We flip it so it looks like this. What is this number here? This is 1 cycle, 1 period. Mm-hmm. So what is this?
2 pi.
2 pi or
pi.
Yeah. So this is pi. And then how tall and like how tall is this? How tall is the amplitude?
You're doing the standard 1-to-1, so it'd be like 2. So the amplitude is negative 3.
Yeah.
Which means the negative means you flip it over the x-axis.
Mm-hmm.
So it would be 6 and 6. Negative 6 to 6.
No, it would just be negative 3 to 3.
Oh, that's right. Sorry. Yeah.
Yep. You're good. So that is kind of how they like kind of relate to one another. So you can see that in moving from just the generic y is equal to sine x into this one, which is y is equal to negative 3 sine 2 theta, our amplitude has gotten taller. So these numbers are larger. It's like a taller graph. I didn't really draw it to scale, but it would look more like this in comparison to this other one, which looks like that. And then we have a shorter period. So if I were to draw these on the same graph, the same line, this one looks like this, and then this one looks something more like, right? So yeah. This one is shorter, like squashed in, and taller. Okay. All right. Can I clear this?
Yeah.
Sweet. Let's do then, let's do number 10. Here we have an equation. It's asking us to pick out the best formula for breathing. So a person breathes in and out every 3 seconds. The volume of air in the person's lungs varies between a minimum of 2 liters and a maximum of 4 liters. Which of the following is the best formula for the volume of air in a person's lungs as a function of time? Honestly, my first thing is I want to sketch this out a little bit. What is your gut reaction when you read this problem? What is the first thing that sticks out?
It's going to go between 2 and 4.
Mm-hmm. What does that mean?
The minimum is 2 and the maximum is 4. So your amplitude's going to be 2.
Yes. What else does this mean?
It's going to be completely above the x-axis?
Yeah. Which, what I'm going for here is going to have a vertical shift.
Yeah.
Yep. So if we call this 4 and we call this 2, this number in the middle here is 3.
Yeah.
So this is kind of like our pretend x-axis.
Yeah.
So I'm going to start building this equation, right?
Mm-hmm.
I'm going to have y is equal to, and then I'm going to have my vertical shift, which is going to be 3. We're calling it 3 because we're moving it from 0 to 3. Plus,
all right, hold on.
y what?
Goes 2. I'm confused where you're getting the 3 from, because if you start at 2, I get that because your minimum's not 0, so it's not going to touch the x-axis.
Okay. I will draw another graph. So.
Oh, 3 seconds? No.
Basically what I'm going for here is that if I start at 3, I have a graph that looks like this.
Okay.
Etc. So I just drew 2 periods, right? If I start at 2, I have, here's 2, and here's 4, right?
Yeah.
So I'm going to say that this is 4 and this is 2. If I say that I have a vertical shift of 2, I have a graph that looks like this.
Okay.
So I'm going to just do the same 2 periods.
Oh, okay.
And so my maximum value would then be 3 if I just had an amplitude of 1. And I drew this a little off. This should be moved down a little bit. So I would have a max value of 3 and a min value of 1. So I picked 3 because it would allow me to oscillate between a max value on my y-axis of 4 and a min of 2.
Okay.
What does this say about my amplitude? So I can call that c is equal to 3. A is equal to.
Well, if your max is 4 liters and your minimum's 2, then your amplitude would be 2, because 4 minus 2 divided by 2.
4 minus 2 divided by 2.
1, never mind,
yep,
sorry.
Exactly. So you were thinking about it the total right way. So our amplitude is going to be 1. So this is going to be equal to 3 plus sine, like 1 sine. And we're just going to use a sine wave because we can here. The only difference between a sine wave and a cosine wave is that one has been moved by like pi over 2 in one direction or the other. We could write this with a cosine wave. We're just not. We're going to use sine here. Okay, so then we are looking at period. So varies between a minimum of 2 liters, maximum of 4 liters, function of time. Oh, breathes in and out every 3 seconds. This is the information we're looking at now.
Yeah.
So what does that mean? Breathes in and out every 3 seconds.
So 3 is equal to b, so it would be 2 pi over b, which is 2 pi over 3 times t.
Is 3 equal to b?
Well, actually, 3 seconds is a cycle, so.
So what is a period equal to?
3 seconds.
Yeah.
1 cycle is equal to 3 seconds.
Yeah. So what is our equation to find a period using b? We say that period
equals 2 pi over b.
So here, instead of like having b, we're solving for b.
Okay.
So I know that my period is equal to 3 seconds. And now I have this equation where I only have one variable. So I can solve for b. So I would multiply both sides by b. I'd have 2 pi is equal to 3b. And I would divide both sides by 3. So I'd end up with 2 pi over 3 is equal to b. So if I say b is equal to 2 pi over 3, then this would be the sine of 2 pi over 3 x or theta or whatever.
Mm-hmm.
And I would be able to verify looking at this little sketch that I drew. I have 3 is C, so yep, this is where my vertical shift is going to be, because again, I'm shifting from this middle line, this 0 line, all the way up.
Mm-hmm.
My amplitude is going to be 1. That makes sense because I'm going from the 0 line, which is 3, to 4, and then down to 2. And then this period is going to be 3 seconds. So this is 3 seconds. T in sec. And I can go ahead and prove that my B is equal, or my B will give a period of 3 seconds by saying period is equal to period is equal to 2 pi over B. And if B is equal to 2 pi over 3, then this is equal to 2 pi over 2 pi over 3. And I can bring that 3 up. So it'll be 2 pi over 2 pi times 3 in the top. These cancel out, and I end up with
3. Okay.
So I've got my period, which is equal to 3, just checked, verified. And the way that I did that was I said, I know how long my period is. I just need to find the B so I can turn this into the equation. And so if this is my equation, then my answer would be B.
Mm-hmm.
Because that is the one that has this equation for the answer.
$31. Can you go over 31?
Yeah, for sure. Okay. All right. So table 1.43 gives values for g of t, a periodic function. Estimate the period and amplitude for this function, and then estimate g of 34 and g of 60. So first things first, we want to, like, in order to estimate g of 34 and g of 60, we're going to use the parts from part A. We're going to try to make an equation.
Mm-hmm.
And the way that I would do this is by sketching it out, which is time consuming, but I think would 2, 0, 14. All right, and it never goes negative. So I'm gonna move it up like this. So we have 0, we have starting at, let's see, we oscillate. Our low point is 11, and our high point is 19. So 11, call that 13. Oh, that's not halfway between these. 17, 13, and then it's in between. So we start here at 14, and then 1 later we're at 19, or 2 later we're at 19, and then 2 later we are at 17, 15, 13, 11, 14,
19.
18. I'm just going to crawl back down. Okay. So we have something that kind of looks like this. Which I feel like there's a better way of representing this, but than like a periodic function. But point is, we're going to represent it using a sine wave. So what is going to be my like quote unquote middle line here? Like what is the point between the high point and the low point?
19 minus 11 is 8 divided by 2 is 4.
Mm-hmm. So it's going to be 4 above 11. So that's going to be 15. So that's right here. So I know that my vertical shift is equal to 15. Then what is going to be my amplitude? You just figure this out.
4.
Mm-hmm. My amplitude is going to be from here to here, from here to here. Amplitude is equal to 4. And then what is my period?
Hold on. 12?
Yeah, if I had something that looked more classical,
yeah,
it would look like this. And so we go from 14 to 14, and then we repeat, and that is at 12, yeah. So my period is equal to 12. I'm going to do this in a different color. So my period is equal to 12, which is equal to 2 pi over b. So I'm going to solve for b. I'm going to say that this is 2 pi is equal to 12b divided by 12. B is equal to 2 pi divided by 12. And get rid of this 2. I can get rid of that 12 and put a 6. So I'll end up with pi over 6. That's my b.
So it would be 4 sine, it's pi over 6.
So my equation would be y is equal to, 4 sine pi over 6x plus
15.
Yes. And then to estimate, so this is based on like our estimations, right? In order to estimate g of 34 and g of 60, we would just say this is y of 34 equals 4 sine pi over 6 times 34 plus 15. And we would just solve. Right?
But just for the tests and stuff, it would just be 4 sine times pi over 6 times 34 plus 15.
Yeah.
Okay.
They wouldn't ask you to estimate what this is. They like wouldn't ask a question like part B. They would just have you do like a part A.
Okay.
So here is the answer to part A right here. And then part B you can find using this equation that we built.
Okay. Oh, I did that one. Sorry, I wrote notes.
That's good.
Can you go over 1.8 on page 63, number 15?
All right. So 63, we're in 1.8. Problem 15, you said?
Yeah.
All right. So here it says use the variable u for the inside function to express each of these as a composite function. And so basically what it's having us do here is say, I need to simplify this into something that I can work with a little bit better. And we're going to be doing this in the future. So if I have a function that looks like a, that says y is equal to 2 to the 3x minus 1, there's a lot to deal with here, having all of that in an exponent. So what it's asking you to do in this problem is say u is equal to 3x minus 1. And u is going to be a variable because u is going to be changing based on x. This is a function. This is u of x. And I can rewrite this then as y is equal to 2 to the u. Because u depends on x, and u is equal to 3x minus 1.
Oh, okay.
So basically what they're asking you to do for all of these is pick out an inside function and an outside function. In this case, the outside function would be 2 to the power of something, and the inside function would be 3x minus 1. So that's how you could approach that. For B, then, which looks like P is equal to the square root of 5t squared plus 10, what do you think U could be that would make this easier to work with? And unfortunately, you don't exactly know how it'll be easier to work with because you don't know what we're going to be doing with them yet. Yeah. But what's like the inside function?
Is like the square root. That's where this one just totally threw me for a loop.
You're good. So if we look at the square root as a function, right, we can have square root of x input output.
Yeah.
So square root of x yields a number. Then this is our outside function. And so our inside function is going to be 5t squared plus 10. Okay. So this could look then like p is equal to the square root of u. So what we could say is that we have this function p of t that we've now turned into p of u of t. That's kind of like what they're going for here. The important thing to remember is inside function, turn it into a different function so that we end up with something that's simple to work with.
Okay.
So what about for part C?
Part C. W equals natural log of 2 times 3r plus 4. So the inside function would be 3r plus 4. Oh, go ahead.
No, go ahead. To just, what is the whole thing going to look like?
U of r. Wouldn't W equal 2 ln of u? Okay.
And so that would be easier to work with in the future, this hypothetical future we're dealing with.
All right.
Just in reality, but isn't right now. Also, just an FYI, something that I have done specifically because of like calculus, they like to use the variables u and the variable v a lot. And so I gave my u's tails. I used to draw my u's like that. But yeah, you need to be able to distinguish between u and v very clearly. So just for future recommendation, make sure you do something that you know that you can differentiate your u's from your v's.
Okay.
All right. It's probably about time to wrap this up. I have another session that's starting a little bit. No, don't apologize. We got a lot of good work done here. Do you have any extra questions?
No, I just, like I said, I just get frustrated because like when I'm doing it and some of it, it's just flowing along and then I hit a spot. I'm like, I just did this. Why can't I undo it?
It's so frustrating. But that's just, I don't, like, unfortunately, I don't really have a cure for that. So
So I'm not alone is what you're saying?
you're not alone. I can promise you that.
Okay.
Sometimes the problems are just like, ugh, where did this come from? And why don't I remember it?
Yeah.
So
That's like, I'm just probably super stressing. Well, I'll let you go. Just trying to figure out how best, because I honestly haven't had to study for a test where I've had to memorize so much where you haven't been able to have at least one sheet of quick reference notes in forever.
a lot of it's just practice so that you memorize these rules and like how to use them. But I mean, like you'll see me even saying, can I do this? I forget my rules of exponents on occasion. And unfortunately for the test, that's not like something that's
Available.
yeah, it is unfortunate. I
Rules
will
of
say that.
exponents, rules of logs.
Yeah.
And I'm
All of
just
that.
trying to make like old school and make like flashcards and stuff just to memorize them.
Yep.
All right.
I use a lot of Quizlet, by the way, in case you were curious. Online flashcards are really handy for me.
Yeah. Awesome. Well, I'll let you go. Thank you.
Thank you so much for coming. Have a wonderful evening.
All right. You too. Bye.
Bye.